Since his earliest beginnings, man's continued existence has been directly linked to the need for more and more energy. This search for new and more abundant sources of power has been one of the central factors of his existence, touching all aspects of his civilization. In the United States today, generating capacity totals about 375 million kilowatts. But in an energy-based society such as ours, the nation's electrical power needs double every 10 years. By the end of this century, the total installed capacity of the United States is expected to climb to 2,100 million kilowatts, more than 8 times the capacity in 1965. To successfully meet these increasing demands for more electricity, the United States power industry has depended primarily on power plants fueled by coal, oil, or gas. At the present time, these fossil fuel power plants account for 81% of this country's electrical power capacity. Hydroelectric projects represent an additional 16% of the total. The remaining 3% is generated by nuclear power plants. But as the power industry installs the additional 1,700 million kilowatts required in the next 30 years, a much larger percentage will come from the heart of the atom. Since their birth on the banks of the Ohio River at Shippingport, Pennsylvania, commercial nuclear power plants have established a proven record of safe, reliable performance. It is a major technological development with a demonstrated overriding concern for public health and safety. By mid-1971, there were more than 20 nuclear power plants operable in the United States. Some 99 more were either under construction or on order. It is estimated that by 1980, nuclear energy will be generating more than 25% of this country's electrical power. By the year 2000, it should meet more than half of the United States power needs. Nuclear power offers not only a virtually inexhaustible supply of competitive electricity, but also a chance to clean up the atmosphere. Their aesthetic design and clean power create very little waste, requiring less storage space for either fuel or waste products than fossil fuel plants. Nuclear reactors produce electricity without releasing any combustion products to the air and pose no environmental threat that is beyond technical competence. As a supplemental power source, nuclear energy can extend the long-term availability of vital fossil fuel reserves. The impetus for the development and application of nuclear power has come in large degree from mounting energy requirements. Public and private electric utilities have based their future on the use of nuclear energy. It has arrived as a complementary source of electrical power generation. U.S. electric utilities have committed an estimated $25 billion total investment in nuclear power plants. An important advantage of nuclear power is its economy of size. The larger a generating unit, the lower the cost of power per kilowatt hour. Utilities have increased rapidly the size of units ordered. More than 50% of all plants ordered during the past 4 years have been over 1,000 megawatts each. Power reactor development in the United States has taken two paths: an early achievement of commercial light water reactors and the development of advanced reactor concepts that promise improved economics and fuel utilization. Nearly all present-day nuclear power plants use light water reactors fueled with slightly enriched uranium. These reactor systems are considered burners, power systems which burn or use the nuclear fuel in greater amounts than the plutonium fuel byproduct they produce. These burners have a built-in limitation on the amount of available energy they can extract from uranium, less than about 2%. One method of increased utilization of fissile fuels is to recycle the plutonium byproduct that is normally generated by such thermal reactors. In 1970, over 330 kilograms of such plutonium were recovered from domestic power fuels. By 1975, this recovered total is expected to increase some 20 times, reaching over 6,600 kilograms. While the most efficient use of plutonium will be in fast neutron breeders, such use is sufficiently far in the future that fuel economics require that the present plutonium be recycled in thermal reactors now, rather than stockpiled. Fuel research has developed methods of recycling the recovered plutonium in present-day thermal power stations. The technical and economic merits of plutonium recycle began in Hanford in 1957, and later in the experimental boiling water reactor and Saxton reactor. The technology has evolved to where large reactor plutonium recycle demonstrations are now underway in Dresden 1, Big Rock Point, and the San Onofre reactors. The initial core of Vermont Yankee will also include plutonium. The demonstrated technical and economic feasibility of such recycling in thermal reactors has proven successful in anticipation of the advent of breeder reactors. Such recycled plutonium programs now open valuable options in management, increasing the usefulness of existing nuclear fuel reserves. But the main efforts to better utilize dwindling fossil fuel reserves and enlist a greater percentage of energy in the atom must come from the development of the fast neutron breeder reactor. The fast breeder operates on the uranium-plutonium cycle and is the logical follow-up in the United States to light water reactors being built today. The principle of breeding more fuel than is consumed could lead to utilization of 60 to 90% of the energy locked in nuclear resources, 30 to 45 times better than with current light water reactors. Assuming a 1986 introduction of the commercial fast breeder, United States electrical energy savings in the following 35 years are estimated to be more than $350 billion. During the transition from light water reactors to breeders, the plutonium produced in light water reactors will be used to help supply both light water reactors and breeders.
A fallback position on the fuel cost as it relates to burnout.
When enough breeders are on the line, they will form a completely self-sufficient fuel system. Light water reactors will then be used predominantly as plutonium burners. Based on its potential economics, the interest of reactor manufacturers and electric utilities, and the base technology already available, the liquid metal fast breeder reactor has the highest priority in the Atomic Energy Commission. President Nixon has stated, "Our best hope today for meeting the nation's growing demand for economical, clean energy lies with the fast breeder reactor." More than 20 years of research and development by government and industry support this conclusion. The evolution to commercial breeder operation is based upon a thorough understanding of the characteristics of plutonium fuel behavior in fast neutron fluxes. But operating in a liquid sodium environment poses problems. What is the possible damage to the oxide fuel? What happens to the metal cladding? How do you control dimensional changes? Sodium impurities? Many of these questions are being answered at the National Reactor Testing Station in Idaho by the Experimental Breeder Reactor number 2 and the zero-power plutonium reactor. EBR-2 is a fast neutron test reactor operated for the past 10 years by the Argonne National Laboratory as the prime United States facility for irradiating fuel samples. Recently, it was modified to increase its operating power to 62.5 megawatts thermal. Much of the existing base of sodium technology needed in the fast breeder program has come from research performed in this test facility. EBR-2 will continue to play a crucial role in the examination of irradiated experiments and promises to yield more essential data on the development of fuels, fuel cladding, structural materials, instrumentation and control, engineered components, and sodium technology. A new essential part of the EBR-2 complex will be the hot fuel examination facility, now under construction. The zero-power plutonium reactor is the largest split-table critical facility in the world, capable of mocking up core configurations of large 1,000 electrical megawatt commercial fast breeders envisioned for the 1980s and beyond. Important nuclear characteristics for reactor fuels and reactor core materials, as well as core design parameters, are being provided from zero-power plutonium reactor experiments. It can accommodate critical experiments for essentially any power reactor by using the largest inventory of plutonium in one critical experimental facility. Data obtained from ZPPR and EBR-2 and other smaller facilities help determine and predict the performance of large fast breeder reactor cores. At the present time, ZPPR is performing a series of critical experiments on large fast reactor core configurations which have design characteristics similar to those of commercial size plants. The Fast Flux Test Facility, known as FFTF, is designed to provide the answers crucial to developing the high performance needed to assure the predicted low fuel cycle costs. This is the key to commercial viability of the concept. FFTF will operate at 400 megawatts thermal with no conversion to electric power. With a fast neutron flux capacity, double that of any other test reactor, the FFTF will produce the necessary effects on fuel and structural materials to be encountered in commercial operation. The FFTF is expected to achieve full power operation by the middle of the 1970s. The objectives of the LMFBR program are the development of safe, reliable, and economic fast breeder reactor power plants for use by utilities, their successful introduction into commercial use, and the fostering of a self-sufficient and competitive liquid metal fast breeder reactor industry. To achieve this goal, the many lessons learned with thermal reactors must be factored into the design, construction, and operation of demonstration plants performing on utility power grids. These demonstration plants planned to operate between 300 to 500 megawatts, would serve to prototype and validate technical understanding, engineering principles, and control systems which demonstrate economic potentialities. The importance of this systematically phased demonstration cannot be overstressed. Many of the engineered components that will operate in a large commercial fast breeder reactor are being tested in the Liquid Metal Engineering Center in the Santa Susana Mountains of Southern California. This proof testing facility is operated by Atomics International under contract with the Atomic Energy Commission. It is providing mechanical, thermal, and hydraulic testing in a liquid sodium environment of many of the components and subsystems that have been designed for breeder reactors. Steam generators, valves, pumps, and flow meters are subjected to approximately 6 times the temperature of boiling water to check their performance. The major government-owned test facilities at the center include the sodium component test installation for testing of prototype heat exchangers and steam generators. For thermal shock testing of sodium components, small valves, equipment, and instruments, a large component test loop has been built. Under construction is a sodium test facility to be primarily used for proof testing pumps, with capabilities up to 60,000 gallons per minute at sodium temperatures of up to 1,200 degrees Fahrenheit. This is the 20-megawatt Southwest Experimental Fast Oxide Reactor, located near Fayetteville, Arkansas. Owned by the Southwest Atomic Power Associates, a group of 17 investor-owned utilities, it is operated by General Electric. The C4 program is a cooperative undertaking among the Karlsruhe Laboratory of West Germany, the Southwest Atomic Power Associates, General Electric, and the United States Atomic Energy Commission. Should unexpected power increases occur in a fast reactor, inherent self-limiting mechanisms will cause an increase in neutron absorptions and will reduce the power increase. C4 hopes to demonstrate this effect in an operating fast reactor. It is the only reactor fueled with plutonium-uranium oxide fuel and represents 8 years of research and development. Operating since 1969, C4 is providing valuable data in support of the design and operation of commercial fast breeder reactors fueled with ceramic fuels. The only commercial fast reactor in the United States is the Enrico Fermi plant in Michigan. It was brought back to service in 1970, following a shutdown for repairs due to partial meltdown of a few fuel subassemblies. The reactor demonstrated operation at 200 megawatts thermal and approximately 60 megawatts electric. The commercial introduction of the LMFBR into the United States economy will require an estimated additional $2 billion+ in government support. An additional $15 to $20 billion must come from the nuclear industry and electric utility firms. Because of the importance of the overall nuclear power program, work continues on several other advanced reactor concepts. The high-temperature gas-cooled reactor, the light water breeder, the molten salt breeder, and the gas-cooled fast breeder. All show potential for improved economics and for conservation of fuel resources, particularly for breeding. High-temperature gas-cooled reactors are responsible for generating almost 2/3 of all nuclear power in the world. The first commercial demonstration of this concept in the United States came in 1966, when the 40-megawatt gas-cooled Peach Bottom Power Station went on the line in Pennsylvania. Experience at Peach Bottom was utilized in the design and construction of the 330 megawatt gas-cooled Fort St. Vrain reactor being built by Gulf Energy and Environmental Systems at Platteville, Colorado. To transfer heat from the reactor core to the steam generator, the reactor will use helium. This will allow the generation of steam at temperatures and pressures high enough to take full advantage of the utility industry's modern generating station technology. Fort St. Vrain is the first American reactor to use a pre-stressed concrete reactor vessel. The PCRV encloses the reactor, steam generators, and helium circulators, all within a single shell. The concrete pressure vessel is strengthened by reinforcing bars and a series of axial and circumferential pre-stressing tendons. A graphite moderator and reflector, along with coated particle fuel, enables the reactor to achieve higher thermal efficiencies and conversion ratios, leading to improved fuel utilization. High-temperature gas-cooled reactors, such as Fort St. Vrain, are the only advanced converters presently offered to the commercial market. The United States effort on fluid-fueled thermal breeders is being conducted at the Oak Ridge National Laboratory. A key element of this program was the successful operation of the molten salt reactor experiment, which went critical with uranium-235 fuel in June of 1965. For the next 3 years, it logged 9,000 equivalent full-power hours. In October of 1968, it went critical with uranium-233 fuel and logged over 4,000 full-power hours before being shut down in December 1969. The follow-up effort on MSRE is a technology development program aimed at investigating the key features of molten salt breeder reactors. At Shippingport, Pennsylvania, advanced reactor research is also looking into low-gain breeders using the thorium fuel cycle. Researchers hope to demonstrate the potential for breeding in an existing light water reactor system. Initial operation of the new demonstration core is scheduled for 1975. If successful, it could provide the basic technology for building light water breeders and converting present-day pressurized water reactors into breeders.
Okay, we're going to start in mode 6. John's the shift supervisor, Jim reactor operator, Paul's the auxiliary operator, and Merlin.
The burgeoning nuclear industry must provide for the training and instruction of highly qualified personnel to staff the new nuclear power plants coming on the line each year.
And you can see how the reactor pressure will increase as you
At the General Electric Boiling Water Reactor Training Center near Morris, Illinois, an intensive 12-week training course is offered to students desiring to become licensed control room operators.
Pressure all the way to 1,005 pounds. Take the increase button and run it all the way to 100%. And you can watch the position indication right here on the stop valve.
From startup to shutdown, instructors initiate all types of normal, abnormal, and emergency situations. Computer simulators recreate exactly what would occur during actual reactor operation.
Your throttle pressure is at 920. As you bring it open here, watch your steam chest pressure come up. Just bump them closed a little bit and watch your steam chest pressure right here. See it come up? Then we can close the lead drains and the steam line drain over there.
Through repeated practice, the students learn plant responses to problems and the steps that must be taken to correct them. Similar control training centers directed to pressurized water reactor nuclear power stations are operated by Westinghouse and Babcock and Wilcox.
Turbine trip rate. As long as we're greater than 1,300 RPM on the turbine.
The essential foundation of any modern industrial society is energy. In less than 25 years, atomic fission has been developed to become a dependable means of electrical power generation. By mid-1970, there were well over 100 United States nuclear power plants in operation, under construction, or on order. Their combined generating capacity is more than 86 million kilowatts. The future energy pattern will be shaped by an ability to meet present light water reactor commitments. And later on, how well we exploit the fuel economies promised by advanced reactors, particularly the fast breeders.